After explaining these general properties of vibrations, I now want to discuss the main bands in the shown infrared spectrum of a microalga and reveal the vibrations that cause these absorption bands. In other words, I will assign the observed absorption bands to the vibrations that cause them. Accordingly, this analysis of the spectrum is called band assignment. As already mentioned, we find the absorption of XH stretching vibrations at the high wave number end of the mid-infrared spectrum. Indicated here are the OH and NH stretching vibrations, which absorb above 3000 reciprocal centimeters. They provide information on the water content of the sample and on the hydrogen bonding strength to these groups. As this spectrum is from a dried sample, the water content is very low. For a sample in aqueous solution, this water band would be the strongest absorption band of the sample. At lower wave numbers, a complicated band profile can be seen. This is still in the region of XH stretching vibrations and can be assigned to CH stretching vibrations. These vibrations are abundant in lipids, and therefore the CH stretching bands provide information about the lipid content, the conformational disorder of the lipid chains, and they can be used to study lipid phase transitions. Below the CH stretching vibrations, there is a large region in the spectrum with very weak absorption from biological samples. The next band is in the region of CO double bonds, and the first band here stems again from lipids. As for the CH stretching band, this band can be used to study lipid content, lipid phase transitions, but also the hydrogen bonding to the lipid carbonyl group. The next band in the CO double bond region is a very important one for protein analysis. It is the Amide One Band here. It is the Amide One Band of proteins, which is caused by the so-called Amide One vibrations of the polypeptide backbone. Several internal coordinates contribute to this normal mode, but the main contribution is the CO double bond stretching vibration of each peptide group. This band provides information about protein content, but also on the secondary structure of proteins, and in consequence also on protein aggregation. We remain in the region of the Amide One absorption because I want to mention one of the problems of infrared spectroscopy. In the same region, also the HOH bending vibration of water is absorbing. In the shown spectrum, there is very little contribution from water absorption because the sample was dried. However, in spectra of proteins in aqueous solution, the water absorption is usually by far the dominating contribution in this spectral region. This is unfortunate and restricts the experimental conditions, as we will discuss later. The next band at lower wave numbers is again a protein band. This band is called Amide 2 band and stems from the so-called Amide 2 vibrations of the protein backbone. This normal mode consists mainly of the NH bending vibration and the CN stretching vibration of each peptide group. Also, this band provides information about protein content and protein secondary structure. It can also be used to study hydrogen bond stability. The next band is also assigned to bending vibrations, in this case to the bending vibrations of methyl and methylene groups. This band is little used for analysis. This is also true for the following band, which can be assigned to another bending vibration of methyl groups. At lower wave numbers, the antisymmetric stretching vibration of PO2- groups gives rise to a prominent band. PO2- groups are found in polynucleotides and in lipids. It is sensitive to the interaction of the phosphate groups with the environment and depends also on the conformation of DNA. Finally, the lowest wave number band shown in this spectrum stems mainly from CO and CC single bond vibrations found in carbohydrates. These vibrations couple well because the frequencies of the isolated bonds are similar. Thus they give rise to delocalized normal modes that extend over a large part of the molecule. These normal modes depend on the structure of the molecule and are thus different for different carbohydrates. Therefore, the absorption in this spectral range can be used to study the carbohydrate composition of a sample. Not surprisingly, the carbohydrate band is found in the fingerprint region of the infrared spectrum, where the absorption is characteristic of the molecular structure as a fingerprint is characteristic of a person. There is also a contribution to this band from the symmetric stretching vibration of PO2- groups, but in the case shown here, this contribution is minor. Nevertheless, this contribution illustrates an important point. In most spectral regions of the infrared spectrum of complex biological samples, several groups from different molecules contribute to a particular absorption band. Thus, the assignments I have just discussed are assignments to the groups and molecules that dominate the absorption in a particular spectral region. This does not exclude that other groups and other molecules also absorb in that region. In this section, I have given you an overview about the main features in an infrared spectrum of biological samples. It is not necessary that you learn all these features by heart, but I recommend you to recapitulate how the assignments in this section fit with the general principles that we discussed in the section before.